If you do not have the standard deviation from the population, that requires that you use the standard deviation from the sample, and as a result, you have a t-distribution. So I've got a simulation I want to show you here in a minute. What we're going to talk about today is confidence intervals. There's not a whole lot to do there, but we do have to talk about a new table and a couple of little things that have to do with it. And then I've got a number of problems that we can work through in class to try to get some of the ideas nailed down. So the first thing I want to do is dig up this example. And this is on Blackboard. So you're welcome to come back here and take a look at it, play around with it later on. This is an applet that's not online, so it should run on most computers. It is under the resources section. So if we go to resources, down here under useful applets, this was not here a while ago. I had looked at a couple of the confidence interval items under here and didn't like what they were doing. And so what I did is I added my own, or added a new one that I found to this. And so I think it's a little bit better in the way of showing things. What this is going to do is it's going to give us 20 simulated samples from a standard normal distribution. It's then going to calculate the confidence interval. We'll put these equations up in a minute here. For this, it's set at 0.5, so it's got an alpha of 0.05. Alpha 0.05 means that if I'm doing 100 of these kinds of confidence intervals, I expect that approximately 95 out of 100 should cover the true mean of the population. We're only doing 20, so this is essentially I'm going to miss 1 out of 20 times. So I would expect that when I do 20 of these things, I would have maybe 1 or 2 of them that shows up, maybe none, that will show up as missing the true mean. So just go ahead and do its thing, do its calculations. So what it's giving us here is 20 different samples. Each sample, it shows the actual values that it sampled from the underlying population. It then calculates a confidence interval based on that sample. So it's based on the mean and the standard deviation of the sample. So it's exactly the equations we're talking about here. And if we look at these, we can see that these kind of bounce around a little bit. As I'm looking through here, there's one that misses. So we got 1 out of 20 that actually missed. So this is pretty precise. So 1 of the 20 intervals that we calculated actually missed the true mean of 0. So it was calculated out here. The other thing to note on these is if you look close, you'll see, for instance, this one right here. This interval is fairly wide. Over here, the interval is quite a bit noticeably shorter. And what's happening is that this wide interval right here, the data is spread out a lot more than it is over here. What's happening is that when the data spreads out a lot more, the value of the sample standard deviation increases. That increases the width of the interval. So the width of the interval is actually dependent upon the actual data itself. If I were dealing with the known sigma case, so if I had the situation where I knew the population sigma, then each of these intervals would be exactly the same size. But since I'm calculating a value for S to estimate sigma from the sample, then the intervals vary in size themselves. That's also why when we're looking at the distributions here, what you're seeing is evidence of why that t-distribution is flatter than the z-distribution. The estimate of the underlying standard deviation for the population based on that sample is clearly variable, and that increased variation causes the distribution to flatten out. Okay. Each time you click play, it'll run another set of data through. This one looks like none of them missed. I programmed a variation on this that I was using before. In the variation I had highlighted the ones that missed a little bit more than this one does.
What do you mean missed?
This is the true population mean here. Most of these straddle that. This one here actually looks like it just barely hits it. They should actually straddle it. In the previous one, there was one that actually clearly missed it entirely. we run this again, maybe we'll see one that misses. Yeah, there's one right here. That one right there misses entirely. So that means that the interval that was calculated is based on this particular sample of data. We're 95% certain that the true population mean lies between these two values. And if we act on that based on this, we would be wrong. So there's always that possibility in this case. Okay, enough with the toys. Now we got to write some equations. So, first thing I want to do is we're going to extend our table. So our table started with a parameter, which was mu. We had an estimate, which was x bar. We had a standard deviation, which was sigma over square root of n. Okay? And that's as far as we got on Monday, right? That was enough to talk about the sampling distribution. What we want to do now is we need an estimate plus or minus multiplier times a standard error to come up with our confidence interval. Okay? We have the estimate up here, so we can write that down. That's x bar plus and minus. And I think the way I've been writing this is the next thing is standard error. I then had multiplier, and then conditions. Because we're getting into doing inference now, part of what we're going to have to do is we're going to have to determine whether the conditions are satisfied for this inference to be reasonably accurate. So, what should the multiplier be in this case? What do you think? Not looking for a number yet. A T star. For proportions, we had z distributions, or normal distributions. We had a z star multiplier that we worked with, because that was a z distribution that we ended up with. What we found on Monday is when we take the sample standard deviation, we need to use a t distribution. So now instead of a z distribution, we're going to be basing things on the t distribution. That implies that we're going to have a t star multiplier. Along with that t star multiplier, we need to know the degrees of freedom.